Welcome, Hornets, and thank you for joining me here today. Today we're going to be talking about sequences from pre-calculus. Now, when we're talking about a sequence, it is different from a function because a function uses all real numbers as its domain. I repeat, domain being the input to a function. Now, sequences, unfortunately, are now working with the whole numbers, more specifically, our natural numbers. Okay, so the natural number set are all of those values that are positive. So we're going to be using 1, 2, 3, 4, 5, all the way up to whatever value we need. And this is the domain of our sequences. And that's very different because the functions we were using all values. That's not the case anymore. And we're going to see that we have a rule called a sub n. Now the reason we're using an a is because we don't want to have an x or a y. We now want to distinguish it from the functions that we've been working with that give us points. All right? So when we're talking about the a's, we're now talking about the actual values in a sequence. All right, so n are the values here. A sub n is going to be what happens when we plug in that n into a given function, and that will then give us our sequence of values. So let's say for a moment that we have a rule, okay? This rule is what we're going to use to create the values that go into the sequence. You'll notice this is a rule that is kind of linear in its nature. We're going to start by taking a 1, and we're going to plug it into the n, and we're going to multiply and add. You'll notice we start off with 7. Then we plug in 2, and we end up getting 9. 3 gives us 11. 4 gives us 13. And 5 gives us 15. And then this would continue. Now, when you're looking at a sequence that's already written out, notice that we can see the gap between the values. And the gap between the values is the number that is multiplied by n. So let's just take a moment and work backward to try to figure out what is the rule that gave this sequence. If I know that the gap between each of the values is a consistent 2. Once again, a consistent, constant 2. And it's happening in our first difference between the two values. Now this is called a tier, and when you have a first tier, you are looking at a linear relationship. Okay, so I can now say that 7 came from some a sub n multiplied by n. Okay, and let's just go ahead and use this as a common difference. Okay, so I'm going to say I have a common difference. We know it's 2. It was multiplied by an n value, and then we ended up adding some other value called a constant. Now, if I take this 2 and I plug it in for d, then 7 has to be 2n plus c. But 7 came from n equaling 1, which means that I can put in the 1, and 7 equals 2 times 1 plus c, which means that 5 is equal to c. That now allows me to say that the a sub n had a common difference 2 multiplied by n plus 5. And this is how we work backward to find the rule. Now we have to be careful because there's a possibility that our rule is quadratic. And when we have a quadratic rule, we'll end up seeing a different group of numbers. For example, let's see if I can come up with one real quickly. Let's take my calculator here, and I'm going to generate a sequence that will be quadratic. I'm going to start with a very straightforward one. And we're looking at 1n equals 2, 3, 4, 5, and 6. So we have 1, 2, 3, 4, 5, 6. Alrighty, so I've generated a sequence, and I'm telling you that we have a sequence that is 5, 11, 21, 35, 53, 75, and it continues infinitely. Now you'll notice we do not have a consistent difference. I added 6 here, but 10 here, then I added 14, and notice this just keeps going. So we're adding 4 at each time. 18, 22, and it continues. We keep going until we get that common difference. Difference of 4, difference of 4, difference of 4, difference of 4. Notice we are now looking at the second tier. And when we have the second tier, it has to be a quadratic relationship. Now, if I'm doing a quadratic relationship, I have to remember what we're doing for a quadratic equation or a quadratic rule. Now, a quadratic rule is not going to have the same difference times n plus t. The quadratic is going to have some common difference times n squared plus another value c times n plus another value, and I'm running out of variables, so I'm going to go a, b, and c just to make my life easier. A, b, and c. Now, this is what gave us those a sub n's. And if I were to make a table of values where I have a n squared plus b n plus c, and I have n equaling 1, 2, 3, 4, so let's say 1, 2, 3, and so forth, what I can now do is plug in that 1 for n and say that I have a plus b plus c. When I plug in 2, you'll notice I'm going to get 4a plus 2b plus c. When I plug in 3 for the n, I get 3 squared times a plus 3 times b plus c. Now, just as we took the difference here, we're going to take the difference here. 4a minus a is 3a, 2b minus b is plus b, and c minus c goes away. Now you'll notice, if I do this one, I get 5a plus b. And this would keep going. If I did a 4, I'd have 16a plus 4b plus c, and this would give me 7a plus b. I'm now going to do it again, just like I found the next difference. 2a, 2a. Now, you'll notice, if I were to do the same thing that I did, so we have our sequence value, so this is our a sub n, this is n. I had the 5, 11, 21, 35. This was, wait a minute, I put that on the wrong side, excuse me. 5, 11, 21, 35, and this is when n was 1, then 2, then 3, then 4. The difference we saw was 6, 10, 14, 4, 4. Now here's the key. This value right here, that is the first value in our sequence, is paired with the first value here in our sequence. The second right here gave us this value. That means that this relationship gives me 6. And this relationship gives me 4. That means that 5a plus b gave me 10. 7a plus b gave me 14. 9a plus 3b plus c gave me 21. And 16a plus 4b plus c gives me 35. Now with this, I can start matching things. Since 5 was made by a plus b plus c, and 11 was made by 4a plus 2b plus c, and 6 was made by 3a plus b, 10 was made by 5a plus b, and 2a gave me 4. I'm going to want to use this information and slowly work backward to find a, b, and c by solving. So if I have 2a is equal to 4, then a had to be 2. If a is 2, then 5, which was a plus b plus c, and 6, which was 3a plus b, I can now replace my a value in each one. This then allows me to solve for b. It's obviously going to happen over here. 0 equals b. Well, that means that 5 equals 2 plus 0 plus c, and 3 has to equal c. Now you'll notice I now know what a, b, and c are, and I can put it back into my sequence, the sequence rule. a(n) squared plus bn plus c. That's going to give me a sub n equals 2n squared plus 0b plus 3. And this is the rule for the quadratic that I gave you at the beginning. Now, be aware, this is how we try to identify rules. And they could be linear, they could be quadratic, or they could be exponential, or they could be a combination of multiples. And we have to be very, very careful about that. All right? So when finding a rule, it's best to first try to recognize what it is by analyzing the information. Okay, analyze the sequence to determine, is it going to be made by a linear? Is it going to be made by a quadratic, as we've seen in the first two, or is it going to be made by something else? Okay? After all, we got lots of possibilities, and anything could happen. That's why this tends to be more difficult. So let's just see if we can't come up with a rule and see about another one. So here's a new sequence. Let's say I have 2 over 3, 3 over 4, 4 over 5, 5 over 6, 6 over 7, ... Notice that this is a pretty straightforward rule, because we're still looking at n equaling 1, n equaling 2, n equaling 3, which is giving me a sub 1 is 2/3, a sub 2 is 3/4, etc. Well, if I'm using 1, that means that this linear on top is made by some common difference times n plus c, and that gives me the top, and then the bottom is made by another linear rule, common difference times n plus c there. So we're going to be looking at these as two separate, 2, 3, 4, 5, 6, ... and 3, 4, 5, 6, 7, ... Now, when I'm looking at this one, this is simply linear, where I take the a sub 1, 1, and I add 1 to it. So a sub n is n plus 1. This one is simply 1 more than the numerator. Therefore, a sub n equals n plus 2. And that's because the common difference was 1. And it made it very easy. Notice, linear sequences are meant to be easy. And we call them arithmetic. Arithmetic. Okay? So we're talking about an arithmetic sequence when we talk about a linear. And there went my lights, of course. Alrighty, so this is working with a sequence. Let's just very quickly review what we talked about. A sequence is a pattern of values or numbers that are created by a rule, and a rule is a function type of object. Okay, so here's like a function, except it doesn't have x, y. Instead of having all real numbers, our n is now going to be the set of natural numbers starting with 1, 2, 3, 4, 5, 6. Okay? Please be aware of that. We then can reconstruct and figure out what is the relationship or the rule by working backward and watching out to see if it's quadratic. Okay? Now, after this, I'm now going to be going arithmetic sequences next. This was our introduction. Thank you very much, Hornets. I hope this helps. If you liked this, please remember to click like. If you have suggestions, please remember, I do like constructive criticism. Please let me know so that I may improve. Thank you very much. Cheers. Bye-bye.